Hello, Ken. Hello, Ken. Can you hear me? Ken? Hello, Ken.
You might be able to hear me now.
Yes. Are you able to see me? You want me to
Yeah, I can
change
see
my
you, but
shirt? Is my shirt okay? Is Are you able to hear me now?
yes, I can hear you.
Is my shirt okay or should I change it?
Sure, it looks fine.
Thank you.
I'm just
I,
setting everything up, so take a moment to get
yeah.
everything
Did you
arranged.
get my slides?
Yeah, I got your slides.
Good. Oh, already lot of people are talking. Thank you.
No, the only one who's talking.
Ken, um, I won't be able to copy the chat as I usually do. Can I request you to copy the chat in case we lose the recording or whatever?
Oh, yeah, I do that. I get the chat.
And then you have a backup recording?
I'm recording it right now.
No, what I mean is a backup.
Oh, the YouTube stream is also recording.
Okay, so we have a backup in case.
Yeah.
Thank you. Any instructions for me?
Just a moment. Uh, just a moment. I'll get this set up. I need to set these things. There, now your co-host.
Thank you. Oh.
So why don't you try sharing your slides?
Yeah. 1 minute. I'm putting it on my desktop. Good.
Well, I was testing sharing.
I will, it does. What happened to sharing
You should be able to share your
here?
co-host.
Um, Is that your copy or mine?
Now you're getting it.
That's my share.
Yep,
How do I go to next slide? Just page up and page down.
try it.
You're
Yeah,
seeing
that should. Yeah, it's changing your slide.
good enough to see.
Yeah, can you do a full screen or is
How
it
do you
full screen? Slideshow full screen.
I view, zoom?
Zoom.
I Zoom does not give me full screen. How does it look?
What are you using here? This is a browser.
I'm opening in what you call PDF in Acrobat Reader. That's not good. I sent you the PDF slides.
Yeah, it looks okay.
This is I can I can't do very much. So what do you want me to do? This is one way, this is another way. Are both showing the same thing?
Yeah, pretty much the same.
Now you are not seeing anything, right? You are seeing my Zoom screen.
Yeah, I see your slide.
You see the slides? So I'll stop sharing or what? How do you stop sharing? Here.
Yeah, a little place to click at the top. So it's recording. No, it's recording and it's streaming.
Thank you.
I mean, I can also share if there's a problem.
Are you
See,
I will not be taking any notes. Are you seeing my screen or
no,
audio?
I'm just showing you that I can share it also.
Very good, very good. Okay.
And I can even go, maybe I can go full screen.
If you want to stay awake during the session, then I can have you put. How do you put to full screen? Does that option exist in Zoom or in Acrobat? I mean Acrobat Reader. Just for 1 minute, I'll be out. 1 minute. आप आ जाना यार आराम से ठंडे में सो जाना हाँ नहीं बाद में हो
We'll be starting in a few minutes.
Nice to see you, Corey and Phil and Alex.
So so how long are you going to be speaking, Robbie?
Oh, I would say about 40 minutes. I would think, maybe less.
All right, so you'll be speaking and then we'll open it up to a discussion. So in the
Thank you.
meantime, everybody is muted.
Okay. Somebody wants to speak something in between, they can raise their hand,
Now raise your
and
hand now.
and Ken will kindly unmute you.
Yeah.
Oh, Phil is welcoming us as well.
I guess we can get started then. Welcome everyone to the Ontology Summit 2025. Today is April 16th, 2025, and we are now beginning the fourth and final track in the Ontology Summit. The track is on ontology and data, and our chair of this track is Ravi Sharma, who is now going to take over and give us a presentation. Ravi?
Thank you. Thank you, Ken, for a very short and good introduction. Our track 4 is beginning today, and frankly, it has been summarized in the overview session, so I will not repeat that information. But I welcome all of you, and I thank Ken for giving this summit very good direction so far, and hoping for future as well. So, are you able to see my slides?
Yes, it
Ken,
looks good.
are you okay? If you want me to increase it more, I can do. This is about the best I can do. So we are going to talk about ontology and data, and we're going to slightly emphasize big data or big data stores and the usual ontology and the usual uh, definition of ontologies, but also this time a little bit of mix of AI in that. And the presentation also uses part of AI and part of uh, ontology and science behind uh, AI works that are getting recognition because of AI. So here we go. This is the outline for the session. Um, are you able to hear me well, Ken?
Yes, we hear you very well.
Thank you. Um, I am taking this opportunity to air some of the pent up feelings about what we need to do more in ontologies as a excuse because I am the speaker today. So, but the main emphasis is as outlined here on this slide, track 4, where they assigned us for track 4 the following. Uh, the third one I requested them and they allowed us to use. So we'll talk for a few minutes each. I hope I don't exceed 40 minutes total. So we'll have plenty of good exchange among us after that. So, what are the differences between mathematics and ontology? We'll talk a little bit about that. Then we'll give examples of 2 or 3 examples of large amounts of data containing ontologies in 3 areas. But prior to that, we will also list most popular and well known ontologies working in medical and earth sciences fields as well as many other related areas. And this year, meaning 2024, has been very exceptional year because AI has been recognized as a tool or agent for discovering new science, especially in physics and chemistry, and we'll cover that. I will briefly give you some idea of who our next two speakers are, and we are also searching for one more. In case you have suggestions, kindly either put them in chat box or communicate with Ken or me. Thank you. We proceed now with next slide. Let me slip. We do see in knowledge graphs some aspect of types of relationships, but we need to formalize the relationships. After all, ontology is about things and relationships, or beings and relationships. So the entities have been adequately covered through vocabularies, thesauri, terms, and so on, dictionaries, and metadata, data, but the relationships have received not as much emphasis, although there is predicate calculus, predicate this, predicate that. So, my request is that we do weights and strengths and closeness, some kind of like Mahalanobis distance or statistical distance kind of computation or something so that can be formalized. Now, Catherine and one more professors have been working at George Mason and other places on uncertainty ontologies. And they are akin to what is being used in AI with stochastic or statistical parameters. So we need to handle that. But I just want to emphasize that there is a method of mathematics or logic, which is common logic or first order logic, which expects you to have exact, almost exact um, notation and formalism, while uncertainties are largely statistical and there is a lot of statistics and physics to deal with that, distributions and supervised and unsupervised learning, etc. We need to emphasize that aspect, and it's coming more in dynamic ontologies. It's my personal orientation, not being a native English-speaking person, I do believe that if we could take the metaphors from Italian, German, Russian, Hindi, Sanskrit, Chinese, and other languages, and then make the AI tools learn the nuances of those cultural richnesses that are of interest to us or used to us, then perhaps our ontology products and services will be more enriched. The last part is, of course, OMG has done a lot, and Mike Bennett is with us, who also represents a lot in OMG, and many of you are also involved in various standards. But the process ontologies are needing more attention, and the BPM kind of BPMN kind of association with business process management. With this, I move to the next slide. So my views are now over. And they are my current views. Tomorrow, if I come and change them, well, you must kindly allow that learning is dynamic. And we don't have only very fixed ideas, we are open to change. Now, I learned this through AI tools, etc. I did not have too much time, but I do realize that mathematics is a formal study of logic, and syntactic formats are used. Proof and computation and formal reasoning, axioms, theorems, etc., are very important for mathematics. While for ontology, description of what is the domain area and what are the entities within the domain. Of course, there are cross-domain ontologies, and Barry and others have talked to us about it in this summit, and we are aware of that. But we largely talk of domain-oriented ontologies in practice. Often they are semantic and conceptual. They do represent knowledge, either through some kind of graphs and knowledge graphs and images and so on. And they have an underlying metaphysics in some ways. We'll come to that. And the memory goes to thank people like Doug Lennett, who spent decades trying to create categories, micro theories, and so on. So this is one, and Todd and others have much more knowledge of what is the foundation of ontologies, and we have talked about some of it in our other tracks of conceptualization. Thank you. Next slide is here. Well, metaphysics is as old as philosophy and thought, documentation of thought or recording of thought verbally, through language, or through visuals. So, metaphysics talks about what the world is, how the world is working, what things exist, and so on. And ontology wonders about what entities exist in the world. So, the world is such a thing that matter is governed by physical laws, is the conclusion of the first two paragraphs. It's a metaphysical conclusion because it describes a way that reality is. Laws are properties of reality. And reality is a kind of reality that can have laws. So, for example, there is a physical law of gravity. At low velocities, it's Newton's law. At high speeds and velocities, it is Einstein's theory of relativity, spatial relativity in space-time, and general relativity in multidimensional space. So that is ontological because it is about a proposed entity. One more sentence about metaphysical concepts in Sanskrit. They, they also pose more questions than they answer, but they do talk of vacuum, non-entities area, entities area, and who and when and how it was created, just as a supplement. Can assign me the task, and I did not know, so but I found a very good paper which is referenced in the references, uh, which is C.C. Zhu. That's how I pronounce it. It's a Chinese name, I suppose. And the paper fully discusses the contents of T box, A box, and how A box can be used to create knowledge base, to create ontologies within the contents of a box, and all of this is happening within the knowledge base. The reasoning is influenced by both the complexity of T box and scale of A box. The neural network model training is done using a Chun-Fi reasoner, and it approximately compiles the logic and deduction process of ontology reasoning, which can greatly improve the reasoning speed while ensuring high quality of reasoning. The large-scale A-box can also be seen as a knowledge graph, and deep learning frameworks and computers help in vector computation. The knowledge graph computation method has high efficiency and reasoning speed, and it scales well for the large-scale A-box. The conclusions are that the OWL-DL knowledge base containing large-scale A-box is becoming more and more common. A-box reasoning has gradually become a bottleneck, restricting its further applications. We will have a speaker on 23rd, next week on Wednesday, namely Alyssa Kendall, who is an authority on standards and OWL and ODM and many related OMG standards, and she will probably expand our questions relating to OWL and relationship with A box and T box. Little more on metaphysics. I don't know why it got switched. This should have come before the next slide, last slide. So please forgive me for the intermix. Somewhere I wrongly arranged. I think we talked about it already. Sorry, the order was right. I was moving slides wrong. Now, do the ontologies adequately support the reasoning process? So, the ability to enable automatic reasoning and integration across diverse systems makes them valuable tools for many real-world applications. However, their success is context-dependent, and challenges relating to scalability, etc., must be addressed to fully capitalize on their potential. Ontologies can adequately support reasoning, but only when designed with formal rigor And they are very powerful, as we know, in biomedical informatics, semantic web, AI knowledge bases, etc. Reasoning will continue for a while in couple of slides. So here comes static modeling, subject to more rigor and adaptability relating to dynamics and uncertainty reasoning. So deterministic reasoning, like OWL, provide clear, reliable outcomes. Here precision is of critical nature. And there are uncertain reasonings for many things in nature, including weather. We have many domains like population, demographics, and so on. We have built-in errors in any measurements of experiments. So here, non-monotonic reasoning is relevant. What are the tools we are using? Mostly OWL, RDF, Sparkle, Protege, and ontology definition meta model, meta object facility of OMG, UML is a language under that, and many others. So many of you are using different tools. I just listed a few. Ontologies with impact making data and domains. So what are the large amounts of instance data in current ontologies? Many of you know more, lot of them. And Elisa will tell you a little more about SNOMED and other um, areas relating to pharma and healthcare that she is developing ontologies for next week. But here is a list, and psych does enter there. Here we are not showing explicitly the EOS DIS, but in the next slide we will show, and we have covered it in our 2 year ago Ontology Summit as a special subject of earth sciences in the pandemics and natural disasters that occur in earth sciences area as well, such as earthquakes, floods, fires, and so on. So there are ontologies for each of these. SOMAD is medical, psych. We are really grateful that Doug Leonard spoke to us a couple of years ago before he is no more with us. Yeah, and so on. There was a lot of work done on linked open data. One of the attendees here is Corey, who has worked a lot on that and on model driven architectures, as he spoke to us last week. And schema.org, I have used it in NIEM, the government standard. NIEM is like a refined ontology which DHS and other law and other domains use. FOAF. Dublin Core is also extended to include federal FGDC metadata, which is metadata standards for federal government in US. So NNGO names, we have had a discussion couple of years ago. So we'll briefly give examples of what the extent of data stores is for the three disciplines shown you on this slide. For earth science, for example, we have 120 petabytes of earth science data as of this year. That 1 petabyte, as I mentioned in the last slide, is 1000 terabyte. Now people have drives, physical drives these days, which go into 5, 10 terabyte up to that level, whichever moving spinning drives, hard disk drives. So terabyte is not hard. It's 1000 gigabyte is a terabyte. So NASA's Earth Science Data Store, primarily located at Goddard, although distributed at Ames, JPL, and other areas for different aspects of Earth sciences. See, Earth includes the atmosphere, ocean, land. Land related various forms, geology, agriculture, forestry, whatnot. So, all of that on Earth Sciences is currently occupying in NASA data stores uh, about 120 petabytes. And standards were developed by us when I was working on the program uh, called HDF. And the HDF standard is now penetrated many more disciplines other than earth science. For example, it has gone to medical area, medical images. It has gone to particle physics area, and HDF5 and various variants of HDF are evolving for different areas of applications. The geospatial data is rather small, a terabyte or so in one place in USGS, but it can contains topo maps and so on and so forth. Very high resolution, that is small scale, large scale, small scale, large scale maps. Google Earth Engine, which also does a lot of mapping job, thematic mapping, where are power lines, where are pipes, where are other structures, towers, and so on, all those, and roads, so canals, that is 80 petabyte as of today. So coming down now, sorry. Are you able to see my slides full or?
So it looks good.
Thank you. Oops. We are okay? I'm unable to move my video panel. It's okay. So there is no single store like NASA's SDIS or Earth Observation System Data and Information System. That is the full load. And the genomic data is the large component, which is the basic component. And you all remember that the variants of SARS coronavirus 2019 made genetic studies very important, very urgent, and really global collaboration happened. And we got very large data stores, but they are distributed in various archives. And of course, the genome project itself was around 200 terabytes, but uh, if you count all of these things, it is in several petabytes, including what data are stored, but they are distributed globally. Uh, Next topic is particle physics. It's the largest, one of the largest data stores is CERN data centers combined together have about 600 petabytes of data storage. This is 3 years of LHC run 3, which generates about, oh, I don't know, lot of data. and it's growing by petabytes every week, I would say. So the plan is that if you combine all infrastructure where particle data are stored, it would exceed about 1500 petabytes. There are some links where, if you are interested, I will be covering some of these areas, but if you are interested, there are better links in this presentation. The presentation will be on the session page shortly. There's some preliminary definitions about particle physics. Baryons are really important in our life. The proton and neutron make the nucleus, but these are also made of hadrons, which include quarks and gluons in various combinations with bosons and fermions. The baryons are fermions. There are a lot of other particles that are also fermions, but they have to have spin half or integral half. The leptons are still a subject of new research in physics. Very strong interest in how the weak interaction interacts with the strong interaction, that is nuclear force, and gravitational interaction, and how the masses are related to neutrino masses of different types of neutrinos. So, the new resonances are therefore interested. They are interesting because they are short-lived, but they do form intermediate aspects of fundamental matter. And Higgs is what made the standard model complete. Although 2004 Nobel Prize went to Frank Wilczek, 2012 discovery made a Nobel Prize for Higgs, who proposed it in the late 80s. But we measured it, the Higgs particle, at CERN in 2012. The time scales for particles or time scales in general, space and time. Space at the minutest level has been studied by people. People talk of point particles, but do talk of strings or superstrings with some kind of one-dimensional string-like extension or two-dimensional strings that contain mass. But the time, if you go on dividing time, what happens? Does it get quantized? Does it become discrete? How small can we measure? It will be covered by Terry Bollinger, our speaker in the May 7th session. So that will be covered there. Now, I come to the last part. If it gets little detailed, please forgive me. I had to cover some, at least minimum part here. Physics Chemistry 2024, first time they received uh, because of AI. The AI researchers received the Physics and Chemistry Nobel. Earlier, only through papers, only through experiments, only through their analysis using math or computation, they got earlier Nobel. But this time, AI helped. So we'll see more details later. And chemistry helped biology through proteins analysis, proteins modeling, and so on. So the physics was awarded to Hopefield and Hinton. And I tried to reach them to see if any of them would speak to us, but this year they are having too many engagements. Perhaps maybe they will come next year and speak to us. Let us hope. We have significantly advanced the AI mechanism itself through their research, through their artificial neural networks. We'll see what they did. And similarly, Nobel Prize in Chemistry was awarded to Baker, Hassabis, and Jumper, the last two being from the Google uh, spin off or Google, another company of Google in England. And they help us predict protein structures for future biology. Uh, Physics and AI. So, what did John Hopfield do? See, imagine we are all used to seeing potential wells, and we are used to seeing stability at the bottom of the potential well, it be Gaussian or any other shape. So, if you imagine a landscape in which there are multiple valleys and hills, at the bottom of those valleys is where energy is minimized, and that is where they have found storage and retrieval of information of interest in uh, artificial neural network associative memory. So that is where Hopfield has created that. The work of Hinton is using Boltzmann machines, which he himself has co-developed, a stochastic, that is statistical neural network, which laid the groundwork for deep learning. And by enabling networks to learn internal representations of data. So these two works are different, but their combination helped us use AI for discovering physics, not only largely in particle scattering data, but in other related physics as well. Chemistry and AI. I'm already at the 35-minute mark. So I will try to do 5 or 10 more minutes. Baker and Hassabis, a DeepMind, the Google AlphaFold 2 solution, is AI model capable of predicting the three-dimensional structure. And I have seen a lot of videos. I have a lot of information on any of these areas that I have stored on my drive. I have seen and tried to assimilate, but cannot share everything with you in this short period. Maybe next year or in a small mini series later in the year, we will try to cover some more if there is interest. So these two works by Baker and Hassabis and Jumper will help us in the transformative part in advancing our understanding of biosystems. Last year, if you remember, Venkat Subramaniam spoke to us from Colombia. He came from Purdue to Columbia, and he has developed a lot of so they are people and living animals. So a lot is happening. I'm requesting you to read the last paragraph. Next slide. This is a picture of the chemistry people. I could have given you picture of the physics people as well, but I'm not repeating too many pictures. So here is my reflection. What is happening through AI in physics? Is the reality itself fuzzy? And therefore we are able to understand that reality? Is that what is happening through use of AI in physics and chemistry? Let's ponder over it and think about it. Or does it imply that current physics and math, as we used to do it, we used to use perturbation for little formal mathematical explanation, create a stable point through math, and perturb the system, disturb it, and see its oscillation, expansion, higher order terms, etc., to reach reality or understand reality within boundary limits of our physics model. The model concept has been discussed by John Sova many, many times. It's foundation of our ontological logical thinking. But the model and reality of real physics, we used to use those techniques and truncate a series. If it gets too wieldy or out of bounds from limits, then we used to truncate a series. Are those things going to disappear with AI? And are we going to live with this kind of new physics? That is something to think about. Also, does it prove that computation is the only way to make progress? So, what happens to our ability to do synthesis? Will we depend only on AI? Or how our synthesis capabilities be used with newer information? And I make one more forecast, in my opinion, and I think many will agree that quantum information will be just like AI. AI is a path breaking area, good for science so far, but we don't know how, like nuclear fusion or fission, whether it will be used for peaceful purposes only. Same thing for AI, we are worried and we hope it will be used for good purpose. But quantum information is also similar powerful area opening. Quantum field theory, quantum physics, we know. But quantum information is qubits and so on, path breaking. Will it be the next area to increase physics and physics knowledge? And will Nobel Prizes be shifting to quantum information researchers in future? That is an open question. Here's a picture of, I like this because kindly look at the cursor. If you can see the cursor or you can see the gentleman standing in the middle bottom of the picture, gives you the scale of the Large Hadron Colliders Atlas detector area in CERN. This is a simulation depiction. It is also reproduced similarly, many similarities before Higgs even was discovered. This is for Higgs, but the discoverer of quarks and gluons and Nobel Prize winner of 2004 is Frank Wilczek again. He used to give talk using Fantastic Realities book with these types of pictures. But it is a some kind of density of events, different kinds of events in Large Hadron Collider. We are now interested in new physics in resonances. The Higgs boson is at top of that discovery, but we have many new things to talk about. People have observed four quarks together, like quark, antiquark, etc. They come in colors, spin, fractional charge, etc. So various combinations of these new resonances are found in scattering data from Large Hadron Colliders. There is discussion about where is this supersymmetry, which is what we think is the next area beyond standard model. So, there are exotic particles that are short lived and they are resonances. Will they play some part like, excuse me, like the um, short-lived isotopes play. When we go for any kind of contrast MRI or CT or something, many times we are given short-lived radioisotopes to go through our body. They don't live too long. Similarly, these resonances don't live too long. Will they play a part in medicine or other applications? We don't know. So, more on resonances. Excuse me. So, machine learning is of two types, supervised and unsupervised. In supervised, we give training set, a small sample representing the whole data in typical form, and then we train all other data and classify it based on that training set. In upper unsupervised learning, we allow data to cluster naturally among them. And these have origins in Michigan and Purdue. Michigan was supervised learning. Purdue was unsupervised learning, and both are useful in earth science data and also in high energy, as you can see in LHC data in this paragraph. More on resonances. The two big detectors that are allowing, I would say, 5 or 6 dozen countries, scientists, to collaborate with each other are CMS and Atlas. And there is a new version of that. More on resonances. They are talking of 59 new hadrons. But in one of my recent papers, we have described low-hanging fruit of these exotic fruits, exotic resonances, 72 in number. 59 are just hadrons, but there are other particles, as we saw. So, future will do a lot on this, just as we did one boson, two boson production, etc., when we were scattering neutron and proton or neutron and neutron together. So, similarly, a lot is happening with these standard model particles scattering each other at high energy and at high
Robbie,
energy.
we should open up to discussion. You're
Oh, thank you. I'm at 45 minutes.
40, 47.
Yeah. Yeah.
Let's
So
let's
that's
get to
it.
discussion.
Well, I will just skip the remaining part of the talk. We have done enough on Large Hadron Colliders. This last slide is references to the works. And the A box reference is right here. C.C. Zhu in MDPI Mathematics 2023. That is the most important one. And two for our next speakers on the summit page for their session on 23rd and 7th May. And last is again first and last with Ken. And second one already covered partly in today. So this is for you. It's always going to be with you. Now, do you want me to unshare the screen or leave the slides here and ask for questions? I already see Gary's hand up.
Yes, Ravi, I do have a question. Sort of, it's about the whole track, since it's on ontologies and data. I'm wondering if the track is going to address some of the hard problems between ontology and data, such as data interoperability. We've had people talk about the role of conceptual models in doing that. I thought that would be part of this track. We've talked about analysis that's needed to unpack things to enable data interoperability. So I'm just wondering whether that's going to be covered, because it seems important
Yeah.
that a
Part
continuity
of it will be
the
covered by
overall summit.
Part of it will be covered by Alisa, but the Bollinger talk will be largely on time and time related parts of ontology. So whatever Alisa doesn't cover, maybe we'll cover in a synthesis session, because we don't have a panel planned for this.
Well, do you agree that data interoperability is one of the big issues between ontologies and data, and therefore should be part of our discussion in a communique?
I took the data to be more generic in the sense of creating things like information elements. There the integration is even harder, because we are crossing sometimes domains when terms overlap domains. So yes, it is a hard problem. We have had one summit devoted to interoperability and one summit on repositories. So we don't know. As time changes, the ontology nature is changing. You see the 9 or 10 ontologies I described, would you call SNOMED ontology a data integration problem, Gary, or something else? There is no even
Well,
conceptual data model there.
SNOMED has a slightly different vocabulary than other health vocabularies, and has always been a big challenge because people are using one and people are using another, how to bring those together. So that gets into harmonization, which was a topic
One of the
that we
topics, yeah.
discussed and I talked about. And I guess I expected that we'd have some of a discussion of that within this ontology and data track also, but I don't see that either.
Well, we can include some of it in synthesis, as I mentioned, because other slots are taken. Any other questions?
Corey, do you have some remarks?
Yeah, Corey. Corey and I have worked together for a year or two on common contracts and common government assignments. Welcome, Corey.
Yes, yeah, it's enjoyed the working together. At the beginning of your presentation, you talked about some of the challenges with the more deterministic representations, such as we have with OWL and even advanced systems like common logic. The physics-related issues that you were discussing later seem to be good examples of that, where a lot of that information is maybe uncertain or probabilistic. What, if anything, have you found to be usable and scalable representations, formalized representations that can be used for that type of information at that scale?
Are you talking of high energy physics, let's say?
Yes, I mean, in all of your examples,
Multidimensionality seems to be one of the key areas, in my opinion, that relates these entities, namely particles and resonances, with the various rules and symmetries that they follow. I would not go to the extent of saying the kind of math, but yes, the kind of math that will address that will be multidimensional, and not only Euclidean, but in multidimensional in many parametric senses. That is one thing I have begun to realize. That's one.
And do we have the tools that enable that?
Do we have tools? Yes.
Do we have
We have
the languages and tools that enable that?
couple of them we have. One we have in traditional, like Wolfram kind of math, and the other one is ancient Vedic kind of math, two kinds of maths that address multidimensionality. And I think perhaps Ken can answer more on that formalism part, but the physics part is definitely we are stuck. We are stuck with single Big Bang business. It's becoming more and more less and less sustainable theory. So either we go to multiple Big Bangs or we bring something else to explain this 75% of what we don't know about matter energy. So, and the high energy is beginning to fill some of those gaps through new particles as relics, as lattices, as point particles, many new theories. We badly need them to explain nature of reality, which is what I call physics. Physics is supposed to take us to real life. Math takes us to real logic, real axioms, real imagination, which drives physics. I hope I can at least partially address what you ask. You are,
Thanks, Ravi.
you are yourself having very great colleagues in physics, I know, who are doing model-driven work with you. But this is a partial answer.
So this is Gary again, if I might ask a question again.
Yes, sir.
Barry Smith and his partner, I'm sorry, I've forgotten the name, argued in that paper that for modern physics, the domain experts, that is the physicists, quantum physics and so forth, don't feel they need ontologies because they have mathematical models that do what they need. And I'm just wondering what your position is on that.
I really enjoyed listening to Barry and Professor Landgrave, with whom he collaborated. Landgrave is physicist. Barry is obviously a philosopher, ontologist, and well-known person in developing top-level ontologies. So they interacted and collaborated on classical physics, and they developed those classical physics-related ontologies, and I refer to them here, if you see in my references, right there on this slide. And they do great theories and models of physics ontologies for classical, that is static physics of past, but not the dynamic physics that we address today, which is only a small part of physics because most of the nature as we experience it is classical physics. We can use classical physics to model weather, for example. But if we are talking of solar flares and solar storms, interacting with that atmosphere, we need new physics, but still within the reach of what they described. So, good question, Gary. Thank you.
Well, I would just add that if you accept their argument, and you can look at it in the paper as well as what he said, it's essentially that they don't think ontologies and the type of things many of your slides were on this area, such as the Higgs particle and so forth. They feel that the way we do standard ontologies is not going to help them and do better than the mathematical models they have. And so my point here is if we're an ontological field, do we accept that or do we have something to counter their argument? And that's a difficult question.
Yeah, I'm going to share only my personal professional opinion on that. I think ontologies can play a part through things like knowledge graph, through things like query within those knowledge graphs, but embedded inside a larger structure of AI, like they did the energy minimization problem in physics that I gave example of. Similar to that, if in the overall solution are embedded ontologies, they might unearth something deep in neural networks that we can't otherwise fathom, because the notion of ontology will create certain patterns within those stores, and we might uncover newer things. This is my personal opinion. I have personally no hands-on work on LHC data, for example. But good question, Gary.
Ravi?
Added to it, maybe, sorry, was someone
Yes,
talking?
yes,
Ah,
Alican
yeah.
is talking.
Uh-huh.
Yeah.
Yeah, it's me. It's me. So my question was that maybe is it something to do with the deduction in a sense that when you use the physics, then you have already the rules. So for example, if you are Newtonian mechanics, then you have the Newtonian rules. But when it comes to, for example, the usage of me, like when I'm using in the business, there are not such rules, and we are relying on the deductive inference. Maybe do you see the nuisance maybe based on the logic, like use of logic in the physics and how the rule-based, so to speak, view of the physics and how they contradict to each other? Maybe it was their argument somehow. What do you think about it?
Very, very deep question, Alican. Very deep question. You are not only talking of validity of rules within a domain like classical physics, but you are talking of portability of some of those rules to other domains like finance, like supply chain where you have worked, and so on. And that is a mind boggling proposition, but someday I think we should have the tools to map from one domain like physics into another domain like supply chain. I wish Ram Sriram or Mike Bennett, somebody to comment on this further. But this is as far as I can go. But very, very challenging question. Thank you.
Ravi?
Yeah,
This
Todd.
is Todd.
Yes.
This is a very interesting talk. Thank you. There's a lot of information I didn't know about. I'd like you to have you conjecture. Might you expect the use of some of these generative AI models based on the data that's being included from the CERN experiments suggest that some of the assumptions, the basic assumptions of physics, for instance, are not necessarily valid?
You mean validate classical physics using the CERN advanced particle data or
Or
invalidate?
maybe even it could be that, or some of the assumptions they make about space and time are just not valid.
Yes, they are beginning to question those very things that we used to assume. For example, we know that Einstein himself has to transition from special to general relativity for certain situations, right, in cosmology. But we we still have assumed the continuous nature of space and time. And by the way, for everybody else listening, Todd and I have also worked together for a couple of years in the EOSDIS project when we both shared our work at Raytheon, Hughes, and so on for NASA. Just to recall my past association with you, Todd. But you know much more fundamentals of ontologies than I do. And yes, the rules discovered there will either break the current knowledge of physics or will validate what still is valid in spite of this massive data. And I might also bring our readers to one realization that by breaking, and more high energy is not everything relevant. Only some relevant things will come out of this. So, like we have so much space exploration, but how much good out of it will come is only in terms of realizable economic, environmental, or social values, and not in terms of debris that we are creating in space. So, so this is my, I hope partially it answers you, Todd.
Yes, thank you, Ravi. Now, I want to make one more comment. Earlier on in your presentation, you talked about the ability to use reasoning with data. And that
Yes,
I took that to mean using deductive reasoning, logical inference with data. And
yes,
it is a problem. If your data set is too large, then trying to draw inferences on it, assuming your data is based or has a representation based on some ontology, is a problem. Of course, it's an engineering problem.
yes.
And depending on your data sets, once you get into, terabytes full of triples, you really can't do the type of reasoning you might like to do. So it effectively becomes an
Yes.
engineering problem. How can you partition your data sets so that you can do reasoning, or perhaps we need better ways to develop or better ways to reason, that is deductive reasoning.
Yeah. The one of the solutions that I found that I described in these slides was that if data is well formed, well formatted, and is within domain restricted within the store that you reason on, then you get better accuracy. If it's more fuzzy and distributed across domains, and you are trying to address all that, one thing is your reasoner becomes slow. And second thing is, you do take advantage of neural networks, etc., and deep learning. You get little better, but then scalability ultimately catches up with you, is what I have
But
read.
as you
Yeah.
pointed out, using abductive reasoning has a problem in that the answers you get may not be valid. And
Yes,
depending on
yes.
your domain, if you're running a nuclear power plant, for instance, you'd want your answers to be accurate, that is, be
You are
precise, and not allow for
absolutely
errors to be introduced that way.
you are absolutely right, and things can go haywire if the model is not fit to the data properly. In physics, we call that way. And in ontologies, it would be reasoning, and reasoning, the logic would fail there. I guess it's rule based logic is better than without rules. So, rules and reasoning are somewhat related. Large data and reasoning always have issues, and neural networks help you reduce that divergence but does not avoid it totally.
Yes. Thank you, Ravi.
Mhm. I'm so glad my colleagues and other listeners are asking good questions, and I'm having a good day, Ken, because I'm able uh, to share my views as you all have seen me learn through this forum a
So
lot.
we have some comments
From
from Doug Miles,
yes, Doug, go ahead.
Janet Singer, Mike Bennett.
Mike,
Well, we'll see if I can unmute and actually be heard. Oh, it's
wonderful,
working. Okay.
wonderful,
Uh,
wonderful.
yeah. So I there there's a philosopher Arthur Young that tried to take things from physics. He had a lot of top domains that weren't really scientific. I mean, a lot of people, got into religion and astrology. But anyway, sticking just to his scientific and math things, he described that a lot of parts could be divided into four concepts or four different distinctions from each other. And then he did that with a threefold way of doing it. So he ended up coming up with like 12 points that you should be able to well, find in physics that would be ontological. That you could say that they will, um, I was calling them bindings or tie points in the chat. Um, and it has nothing really to do with physics more than how we describe things to ourselves and to each other. We we're just, but it ends up corresponding to the equations of physics. So anyway, I feel like there's an ontology in there somewhere. Why those 12 things end up realigning to the other 12 things, to similar things.
Definitely, physics is driven by metaphysics, science in general, and metaphysics and philosophy drive.
Mm-hmm. I guess where I was going is, when you look at the equations, they're reused everywhere. Distance, rate, time, whatever that one. But there's like circular, angular velocity equations that pi gets involved in, and there's nowhere that you're looking at you see pi, but the universe moves like that. And so, are those points of where an ontology belongs things that
Yes.
react to angular motion?
Yes, yes. And we have been only using one kind of coordinate system or Euclidean only. There are obviously many other types of geometries that affect us. And you are right, pi is just one of them. Ellipses are other ways of understanding rather than circles, and so on and so forth. Catenary, uh, the uh, the various other kinds of shapes. Oh, wow. You look at the motion and precision of our planet, the moon, and how to look at the visual area of moon from Earth or the eclipse, etc., the complications. And then GPS, uh, generating a good geo model is itself horrendous in terms of maths. So you are right. It is details. We have to look at other ways. Theta phi r is one good coordinate system where astronomers are happy, and they are happy to talk of parsecs or arc seconds and so on and so forth. Great question. Thank you, Doug.
Mike or Janet?
Yeah, I think this is a good track to bring in the Barry and Jobst issue of the connection between ontology, mathematics, and physics. The issue that they came across was sort of the edge case of, in their language, they said that they couldn't map the concepts in the mathematics that were useful for predictions to common sense entities. And so I think that's a really good thing to keep in mind throughout this track about the data. We can make measurements and we can use the data and we can do things that we don't quite understand. This is another case of the failure of explainability, that when you try to interpret quantum mechanics, for example, you end up with a lot of different conflicting world models. And so anyway, just glad that that's been brought up again, the Barry and Jobst question, because
And
that's sort of...
the very first slide, Janet, first part of your comment I want to ask, it questions how are math and ontology related?
Right.
And when it comes to logic and accurate logic, I sort of see it the way John Sower describes us. And then when it is fuzzy, I get little lost. And they say, even when AI I use to search, that math is one thing and ontology is another. And they're not necessarily the same. So we can't
Right.
say
I guess that issue also came out in was it Gruninger's presentation about Hilbert's problem and the mathematics and ontology. So it'd be great to revisit that and keep it in mind. What does a mathematical model have to do with an ontological model? Right.
Very good reference to Hilbert space, because
Right.
all of this physics does assume Hilbert spaces. Of course, he talked of Hilbert theorem, which is different than Hilbert space, but by the same person. So he influenced a lot of areas.
Mhm.
Thank you. Hilbert, Fock, and Dirac. They did, and Wigner. 4
Right.
people. Thank you. And can help me discover one more. In German, it was invariant variants or something by a lady, Noether's
Mhm.
theorem.
Right.
Right.
Oh, yeah.
Thank you, Janet.
Mike, are you still there?
Yeah, I'm sorry. It wasn't so much a question, but I was kind of riffing off of something that Douglas Miles said, a choice of language there about having to glue the mathematics to something and binding to things. And this might be part of the answer to how is ontology and mathematics related, which is that actually the interesting question is how is each of them able to be related to reality or to data or to whatever else they're about. So it's sort of like binding with computers. We've been exploring this. Jim Logan has a nice example where you have your name and social security number and so on, and they're all data. Then you walk into like the DMV, the office where you go to register a motor vehicle, and the clerk looks at you and looks at the data and says, "Yes, that's you." And at that
We lost you.
So this is Gary again. I also had a response to the idea of binding. So there are 3 things I think to think in the binding. The original thing that was mentioned was from vocabularies to reality, but in between is ontologies essentially that try to help that bridge, and that takes you into the whole realm of you have a term, you define it, ontologies then try to put axioms to the definitions, and then that is hopefully a good approximate model to the reality, but it has to again be based on the truth makers. We didn't get into that here, but we had prior to it. So the degree to which there's a good relationship, one argument is to the degree to which things like the vocabulary with its definitions as formalized in an ontology map to truth makers or bind to truth makers.
And terms and vocabulary are highly language dependent.
Right.
Thank you.
Also, yeah, so Ken's presentation on the unreasonable effectiveness of mathematics, I can revisit
Yeah.
those ideas. Yeah.
Yes. Was very good.
Yeah. Has anybody bothered to look at like data.gov?
Yes.
I mean, talking about large amounts of data.
I think
To what extent is it easy to access any of that data? Not just get the data, but make sense out of it. So what does that mean?
Well, 20 years ago, when I was still working and involved in some federal efforts, data.gov got started, and I, along with some others who were involved, said, you know, you need to add some semantics. You can use RDF. And they said at that time, this is a big effort. We don't have time to do that type of thing for now. Maybe we'll get to it later on. I think schema.org is sort of a lightweight approach, attempt to sort of add that. And then we heard from some of our speakers, Giancarlo as an example, about the problems you get when you're too lightweight and you can't really support adequate data integration and harmonization. So, you know, that's where I think we are still.
Corey,
Yeah, that seems to be where ontologies would be important, not so much determining, the mathematics behind the data, but just, what is this data? I mean, where does it relate to?
Yeah. Or what does it
Think
mean if
about-
you
Just
use-
about
Think about
15.
these detectors they have at CERN.
Yeah.
The amount of engineering that goes behind those enormous detectors is enormous.
The hope I always had when I was working in these fields in healthcare and other things was that you could at least get a little pilot program to show you the value of this thing. I mean, so they were, spending a fair amount of money. They didn't want to sort of semanticize everything. But if you could take a piece of it and show the value of that, then maybe over time, incrementally, you might get this in there. But that is still not happening well enough or strongly enough. And again, there's a lot of financial issues now.
Yeah, the conversation that you and Gary are having, Ken, is to be addressed really by Corey. Corey, you are familiar with linked open data. You are familiar with CIO's effort from Vivek Kundra and Chopra's times at White House.
Yeah, and data.gov.
The data.gov, right?
Yeah.
And our colleague at HHS helped us also in populating that. So kindly tell us a little more about that. Thank you.
Well, one thing I thought I had when discussing data.gov, and any of you who have worked on enterprise ontologies recognize it as a social political process, right? It is not a purely scientific one, unfortunately. It involves collaboration and agreement. If you look at something at the scale of data.gov, there is no entity with the agency to organize such a process. And we know the difficulties of political processes in the first place. So one of the things that we lack is the ability to have things to reuse. And while there's been interesting work on domain ontologies, upper ontologies, most ontology efforts start with a blank screen or a very small screen and start to type in words and definitions, rather than bringing them together from some one or set of existing corpuses. And
so to answer Ken and Gary, are these data.gov sites being updated periodically and correctly, or are they kind of disjoint in a way?
They are totally disjoint. They're just generally a set of spreadsheets, largely uploaded, where the columns of those may or may not be well defined. Sometimes they have reasonable English definitions, but there's no attempt for a semantic underpinning. There was, in the original concept, work on bringing them together with some common ontologies, but that has fallen to the wayside. It's just a data swamp for all intents and purposes of
Oh my goodness. Thank you. I expected that to happen over time.
Was there originally the belief that a tool like Psych would be able to be used on these things? I mean, without a tool like that, it would be hard to do things with as much data and everything that there is. I mean, is it still
very good question, Doug. I'm interjecting in between. I think just as we have LLMs dealing with large text stores, we need to think a little bit about how this plethora of data, which are reasonably somewhat organized, somewhat disorganized. How can we pull? Can AI tools pull something out of them using neural networks or something on data? And that now answers a very big question that Gary had asked in the beginning, is where are we? with respect to data and ontologies. So maybe AI would help. I don't know. Any thoughts of LLM like data, something like we do
I am
with
actually
text?
concerned with the over expectation of what LLMs will do for data federation, rather than, there's hope that they'll assist, but the
I did not
attitude
mean
in
applying.
enterprises is it's magic and it's just going to solve our problems and we don't have to think about these things anymore. It concerns me.
No, I was not implying that we use LLM model. I was saying something like LLM, but more related to aggregation of data. We were hoping at one time that data would lead to information stores, and has not yet happened fully. Happens in weather, obviously, because we get weather forecast. So there are some fields where it's happening. There's medical directives, so that way health directives, but it's not happening on all data at the federal level in US alone, let alone globally.
Yeah, that raises the issue of the provenance of the data. What were the intentions, the assumptions, the measurement instruments? How is it encoded? All of that side, where ontology would be useful, because it would refer to the human activity that generated the data. So I guess there's really no excuse for not having ontology on that side, as opposed to the mathematical model side.
And we are constantly generating those in, at least for our various departments that serve the government purpose. But Corey has brought the reality to light. I was not updated on that for last few years, so thank you.
Yeah, out of curiosity, I looked up, I did a search for metadata management on the data.gov site, and I got, like 4 hits.
FGDC metadata
Doesn't look
is
like
one of,
a lot's happening there.
but do you see FGDC metadata group? Federal government's metadata group? No, which is a evolution over Dublin Core, I thought.
Yeah,
And
Dublin Core is mentioned.
is EOS DIS metadata mentioned?
I'm just, it
Or
doesn't
Earth
seem like
Science?
there's much going on in the way of metadata management for this data.gov
And
resource.
healthcare can use a lot of metadata.
That's just data.gov. I mean, that's not all of science. Anyway, we're running way over time.
Thank you, Ken.
We'll have to continue this discussion later. Thanks everyone for coming.
Thank you,
Ken.
Ken, and all my colleagues who are on the call. Thank you so much. I
Thanks, Rob.
deeply appreciate
To
your listening
next
to me.
week when
Yes, Elisa
Lisa
Kendall will be speaking to us. She is from OMG and also thematics, and she'll talk a lot about the gaps that I have in my knowledge that she knows a lot more about, and I've worked with her for a couple of years in OMG working groups. Thank you so much. She will be a very good speaker. I request everybody to advertise and come to listen to her. Ken?
Okay, so please
Back
come
to you.
next week and